Hi students, this is one of the important and core subject, digital principles and system design. It has the 5 units. In this today's session, we are going to start with the first unit, Boolean algebra and logic gates. And this is Professor G. Ilangovan, Department of Computer Science and Engineering in PR College of Engineering and Technology. And these are the uh, books you can refer at any moment, uh, and beyond the syllabus and all the things you can refer. And usually we used to refer Maurice Menu is the one of the Bible for digital electronics, and it is now with the enhanced version is available, or else you can refer the Charles Roth or John Wackerly. So these three books are very good. This is also recommended in your Anna University syllabus. And what we going to learn in the first unit is it's going to be the Boolean algebra and logical gates. In this, we are going to discuss about the number systems, and with the different numbering system, what will be the arithmetic operation involved, and different kind of binary codes, and how we are using the Boolean algebra. For that, we understanding the basic concept, and of course the using the Boolean algebra to implementation purpose, we are getting understood about the basic purpose of logic gates, and what are the theorems available, and how we are establishing a Boolean function, and from that the standard canonical forms, and the simplification of the existing Boolean function using Carnot maps, and how we are going to finally implement in the logical gates, or how we can implement the same thing using NAND and NOR gate alone. This is the entire scenario you are going to understood after completing the first unit. In today's video, we are going to discuss about the numbering systems. So under the numbering system, we get introduced about that numbering system, and what are the digital systems and binary numbers available, and we understood the basic difference between analog and digital signal. And of course, in the numbering system, we will start with the very basic and conventional numbering system called decimal number systems, and the special numbering system, octal number systems, binary number system, and hexadecimal number systems. And these four, after reading these four numbering systems, we get uh, we are going to analyze how to convert from one numbering system to the another numbering systems. And once we are coming to the to understand about the thing, which one we will be calling as a digital system, whether we have the digital systems in our environment. So in a day-to-day life, we are using the maximum number of digital systems. You turn around the world, wherever you go, you can see the number of digital systems. For example, the what we are using, the laptop or the mobile phones, uh, washing machines, and iPads, and uh, audio video players. So like this, everything comes under the digital system. So we have to understood which one we will be calling as a digital system. So for that, we need to understood what is a digital and what is a system. A system is will respond for any input. It is going to give a responded output. So this is going to be a kind of system. So where we are giving the digital input, and it will process, and it may produce digital or analog output. And if you are seeing the uses and application of the digital system, as I mentioned, in this current world, we'll be using everything as a digital systems or digital environment. And uh, usually, if you are saying the digital, the basic fundamental thing is the binary digit. A binary digit is called as a bit, and it will be having only two values, either 0 or 1. So with only those two values, it is going to uh, uh, the entire system is going to use only zeros and ones. and where we are giving the zeros and ones, we are calling as a digital systems. And when we are going to use the zeros and ones as sequence, and we need to classify it into categories, so that's what we are calling as a bytes, nibbles, words, like that. So when we are having the more than one bits is going to be collected and is going to be represented in different way, is called as the binary codes. And when we are saying, as I mentioned, the digital signal, that means uh, we have the different kind of electrical and non-electrical signals which day-to-day life we are using. Say the electrical signal is what is the voltage, current, frequency, and non-electrical signals like pressure, weight, uh, humidity, this kind of things. So these are all the things to be converted in the digital forms. So the digital signal will have ones or zeros. The ones usually will be represented as a high level or edge, or it is available on. And similarly, the value of zero logically will be represented as low or L, or there is no such signal. So it's an off. So we can say zero. So conventionally, in different cases, the logic signal ones and zero will be represented as high or low or on and off. For the mathematical purpose, we used to represent somewhere else H or L, like that. So the digital system using only zeros and ones. So it has only two values. So that's what we used to say it's a binary system, because binary in the sense it has only two. So that's what we are having. The digital systems is we are saying that it has the binary values. Say you see the conventional switch, where everywhere you will be seeing on and off. You can see on the switch I and O will be there. So you can read it as a 1 or 0 also. The I stands for the in, O stands for the off. So that's what the digital representation will be there. And the George Boole is a mathematician, is involved in this developing the digital era. It started in the 1847, and along with another scholar, Claude Shannon, they have contributed much in developing the digital environment. So the development of digital environment leads to the digital calculator, it leads to the digital computer. So now we are having the sophisticated computers. And from that digital environment, it has been developed in computers. Before developing the computer, it was the development of the microprocessor and microcontrollers. It has the revolution in the digital world, because it came with the programming capability of with the zeros and ones. So it makes a great revolution in the industry and in the world itself. And parallelly, the semiconductor development is also helps for the development of digital field. uh, so from the digital system, we can understood that the telephone, digital cameras and calculators and all much more things, these are all the digital systems, as I mentioned already. So once we are saying about the digital signals, the physical phenomenon, the physical signal what we are having is an analog in nature. So as I mentioned, the pressure, weight, humidity, so speed, velocity, this kind of things and all is in analog in nature. So even the electrical signals is in the nature of analog signals. So this signal to be converted as a digital ones and zeros. For that, we will be having n number of techniques available for the conversion of analog to digital. And the conversion of analog to signal is out of our scope. So we will be considering how the analog and digital signal is there. So in the left hand side, the signal shown is in analog format. It's a continuous varying with respect to time. And the second one shown is the digital signal. It is the discrete in nature. So that means it is not varying with respect to the continuous, but it has the different kind of amplitudes. So that also is going to be reduced, and it is shown the comparison between analog and digital signals. And when we are coming to the binary digital signal, the discrete signal is going to be changed as a digital signal. So with the only two values, low and high values. And so to understand the digital principles, first we have to understood about the different kind of decimal numbering systems available. So the our day-to-day life we are using a numbers, so that will be called as the decimal number system, the conventional number. Why we are saying it as a decimal number system is it has 10 different symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 to 9 we will be having 10 different symbols. So that's what it will be called as the decimal number system. Deci means 10. So this number system will be calling as its base is 10. So whenever you are saying base is at 10, so it has 10 different symbols. So likewise in any numbering system, if you are saying the base is 7, so that means it's going to have 7 symbols. And scientifically the base is also referred as radix. So this was the 10 different systems. And when we are going for the collection of more digits, and we will be saying that each position is going to have its own fixed positional values. For example, here I have shown 512 and 74. So here the 5, if you are taking 512, the number positioning 2 is the ones position, and 1 is in tens position, and 5 is in hundred positions. So this is our conventional number system. Scientifically, when you are going to relate the position value with the base or radix value, the 10 power 0th value, and 1 is 10 power 1 value, and 5 is 10 power 2 value. By assuming that after 2, the right hand side, there will be a decimal point, a fractional point. After the fractional point, there will be a 7 and 4. The 7 will be represented as 10 power minus 1, and 4 is 10 into 10 power minus 2. So from this we can understood that from the decimal point, while we are moving towards the left hand side, it increases in the positive value starting from 0, 1, 2, 3, 4, 5 up to n. And in the right hand side to the decimal point, it starts from minus 1 and keep on is decrementing minus 1, minus 2, minus 3, like that. This will be common for any kind of numbering systems. So this is for the decimal numbering systems we are using. So to calculate the conventional magnitude, what will be the value of the any numbering systems? Since uh, we are more convenient and we are experienced with the conventional base numbering systems, so we have to understood how to convert the any value with the decimal number system. Then only we are able to understood what is the original value of that. So for that we'll be starting with the decimal numbering system itself. So to calculate the each values 5, 1, 2, 7, 4, each positional values, 5 values into 10 power 2, and 1 value is 10 power 1, and 2 value is 10 power 0, 7 value is 10 power minus 1, 4 value is 10 power minus 2. So if you are putting all the things, you will get 510 to 0.7.004. And if you are summing all the things, you will get 512.74 with the base 10. So in the digital system, whenever we are going to represent the numbers, it is the best method of representing with the base value, because we'll be having different numbering systems. To avoid the ambiguities, we are always representing the number with the base. And the next most useful numbering systems in the digital environment is the octal numbering system. So here the base is 8. As I mentioned, if the base or radix is 8, means it is going to have the 8 different symbols. The symbols are 0, 1, 2, 3, 4, 5, 6, and 7. And its positional values, as I already told, from the decimal point, and each position from the left hand side, it will increasing from 0 to 1 with the base power. So the positional value 2 is 8 power 0 is 1, and positional value 1 is 8 power 1 8, and positional value for 5 is 8 power 2 64. And similarly, right side to the decimal point, 7 is the 8 power minus 1, so 1 by 8, and 4 is at the base of 8 power minus 2, that is 1 by 64. So to find out the h values, we have to multiply that thing. So 64 into 5, 8 into 1, and 1 into 2, and 1 by 8 by 8 into 7, 1 by 64 into 4. So in conversion, in octal number, we will be saying 512.74. If it is octal, its conventional, its decimal value is 330.9375. And for example, we will understood the conventional methods. So the 512.74 in in the octal method should be represented as like this, the base 8. So its conventional value is 330.9375. And the very most popular and the effective numbering system till date is the binary numbering systems. So with the basis 2. So that means it has only two different symbols. That symbols are zeros and ones. So only two values, the two bits. So the each positional values is going to be 2 power 0, 2 power 1, 2 power 2 from the decimal point or fractional point towards the left hand side. And similarly, when you are moving towards the right hand side, it will be 2 power minus 1, 2 power minus 2, and so on. So if you want to get the its conventional equivalent with the base, so similar to that, the position values to be multiplied with that value. So the one value is 1, and zero value is 2 to be multiplied by 2, and the leftmost one to be multiplied with 4. And similarly, in the right hand side of the decimal point is the 0, and it should be multiplied by 2 power minus 1, and the 1 should be multiplied by 2 power minus 2. And one thing is, in binary system, the decimal point we are saying that should be mentioned as the binary point, no more decimal points. Since we practice with the decimal points, I used previously it as a decimal points, and here from now onwards, we will refer binary points wherever it comes in the binary numbering systems. So its conventional value is 5.25, and for the binary number value of 101.01. So this is the formal representation of the binary values by representing the base value. And the additional information here is, whenever we are grouping four number of binary values together, that collection will be represented as nibbles. And when you are collecting 8 such bits or 2 nibbles, will be called as the bytes. And the next numbering system is the hexadecimal number systems. So its base is 16. So the name itself says that deci is for 10, hexa. So hex, that is 6. So hex plus deci, that is 16, is the base for the numbering system. So that shows that it has the 16 uh, uh, figures to represent the numbers. But in our conventional methodology, we will have only 0 to 9, 10 digits. To have the remaining 6 digits, we'll be taking the uh, figures from the alphabets. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After the 9, A, B, C, D, E, F. After F, it will be counted as 1, 0, like that. And its positional values similar to that. From the hexadecimal point, left hand side is 16 power 0, 16 power 1, 16 power 2, and from the hexadecimal point, right hand side is 16 power minus 1 and 16 power minus 2, like that. So to have the original values, and E represent the 14. So if you are converting into the conventional number, it will be comes like this. And don't worry about that, the conversions and all, we are going to concentrate again how to convert from one number to another number. Now you just understood the different numbering systems exist. So the equivalent hexadecimal number, what we are given is 1E5.7A, and if you are converting it to our conventional number, it will comes as the 485.4765625. And for we will be many times we will be coming across the powers of 2. So that's what the standard powers of 1, like that. And if you are seeing the key values, 2 power 10 is going to be 1024, and we will be saying the 2 power 10 as the 1 kilo. So that's what 1024. So if you are saying 1024 is a 1 kilo, the 1 kilo comes in the 2 power 10. And if you are going for 2 power 20, you will get an 1 mega. So similarly, if you are going for 2 power 30, that will be an 1 giga, and 2 power 40 is an 1 tera. So like that, the powers of 2 will be multiplied. And this is a simple example. So is it possible to convert 365 to its equivalent decimal value? So how we to do this? Just simply multiply the each positional values. The positional value for 5 is 8 power 0, that is 1, and positional value for 6 is 8 power 1, that is 8, and positional value for 3 is 8 power 2, that is 64. So each digit need to be multiplied by its positional values. So if you are doing so, 3 into 64 plus 6 into 8 plus 5 into 1, so you will get 245 with the base value as 10. So this is a simple reminder how we have done the conventional methods. And now, as I mentioned, we have the four different systems. You see that we have discussed decimal number system, octal number system, binary number system, and hexadecimal systems. And decimal with base 10, octal with base 8, binary with base 2, and hexadecimal with base 16. Now there is a requirement to convert from one number system to another number systems. So we need to convert from octal to decimal. Just before we have seen an example. So we have evaluated the magnitude, and similarly from the binary number system to decimal, we will be evaluating the positional values and multiplying that. And similarly the hexadecimal to decimal will be evaluate the magnitude. So if the system is octal or binary or hexadecimal, we'll be multiplying its positional values and finding some, we'll end up with the decimal numbers. But from the decimal to octal or binary or hexadecimal, how to reach? So that is the thing we are going to concentrate. And similarly, from binary to octal, binary to hexadecimal, or hexadecimal to binary, or octal to binary. So how we are going to convert that, that we are going to see. So if you are seeing this, it is possible to convert from any number of system to any other number of system. The conversion we need to understand that one, then only we are able to do the better system design development. So the first thing is we wanted to convert the decimal number to binary conversion. So each conversion is capable of easily by doing a successive division by the base value 2. So any numbers, if you want to convert, so from the decimal, you convert, make the successive division by the base value. So the 13 is given. So to convert to the binary value, we'll be dividing the base value 2. So quotient is 2, remainder is 1. So we may get either 1 or 0. That is going to be the first coefficient. And the remaining value, the 6 is going to be again divided by 2, 3. Now the remainder is 0. Now that is going to be the next coefficient. And now the quotient is 3, that is greater than base. So whenever the quotient is greater than base value, we will be repeating this process. So we are dividing it by 2. So quotient is 1 and remainder is 1 and coefficient is going to be 1. So the quotient is 1 less than the base. So we'll be stopping the process. So that means we are getting that 0 only. So it reaches 0. So finally we'll be getting the values. So this will be 13 will be represented as 1101. So this is how we'll be doing the conversion from decimal to binary. So only the thing is we will be doing with the successive division of the base value till reaching the 0 or less than the things. And here we wanted to mention the two, introduce the two terms, most significant bit and least significant bit, that represent weightages. So the coefficient A naught is going to represent LS, least significant most significant bit, how I'm going to multiply the by the base, we take the resultant as the coefficient. So we take the 0.625 as an example. We take 1.25. 1 is the integer that we consider as the fractional part 25, and that is going to be taken and multiply again, and we are going to repeat till ending the 0, or how much the people can pay. Accordingly, we will be doing. So 0.25 into 2 will be getting 0.2. Coefficient is going to be 0, and fractional point 5 is again going to be multiplied by 2, and 0. So we get